Hello everyone. Today we will start our new chapter, Solid State of Class 12 Chemistry, Chapter 1. In this chapter, we will learn different possible arrangement of particles in solids, correlation between the nature of interactions within the constituent particles and properties of solids, and structural imperfection due to the presence of impurities. So before starting the lecture, please like the video, share it, and please subscribe the channel. Thank you. First of all, as we look around, most of the things we see are solid rather than liquid and gases. The solids are the substances which have definite volume, definite shape. So there are certain characteristics of solid state. Let's start. First of all, solids have rigid and definite shape. So solids have fixed shape, but liquids and gases don't have fixed shape. So very characteristic of solids are rigid and definite shape and mass. Next one is they have rigid shape and definite shape, so they have definite volume also, irrespective of size and shape of container in which they are placed. Intermolecular forces and distances. Intermolecular distances are short because the particles are closely placed. They have a compact structure. The particles are closely placed, so they have a compact structure. That's why their distances are very short and their forces are strong. The constituent particles of solids, they can be atoms, ions or molecules. They have fixed position and they can oscillate about their mean position only. So they are fixed, they can't move from one place to another, so they can vibrate or oscillate about their mean positions only. They are incompressible as they are hard, rigid, definite shape, so they can't be compressed. They are incompressible. Next is density of solids is greater than liquid and gases. They are heavier than liquids and gases. They have high density. Next is solid diffuse very slowly than liquids and gases because the particles are fixed at particular place. So they can't move from one place to another easily. Or we can say the movement is negligible. So they can diffuse very slowly, or we can say they don't diffuse. Next is classification of solids. Classification of solids, we have classified solid into two types, crystalline solid and amorphous solids. Solid can be classified on the basis of nature of order present in the arrangement of constituent particles. As we have already studied, the constituent particles can be atoms, ions or molecules. Therefore, there are two types of solids, namely crystalline and amorphous. Let's see what they are. First, in crystalline solids, they have definite characteristic shape. They have a particular shape. In amorphous solid, they don't have a shape, so they have irregular shape. In crystalline solids, they are long range order solids, whereas amorphous solids, they have short range order. We can say they are less ordered than crystalline solids. Next is regular arrangement. The constituent particles are arranged regularly, where they do not have a regular arrangement of constituent particles. Next is in crystalline solid, the sharp and characteristic melting point is formed, whereas amorphous solids do not have sharp melting point. They melt over a range of temperature. They don't have a fixed sharp melting point. They melt over a range of temperature. Next is crystalline solids are anisotropic. This is very important point, students. Different physical properties in different direction. They have different physical properties in different direction. This property is called anisotropy. Crystalline solids are anisotropic. Next is amorphous solids. They are isotropic. Same physical properties in all direction. In every direction they have the same physical properties. They show isotropy. Next is in we can say crystalline solids have particular all the important characteristic of solids, so they are true solids, while amorphous solids are pseudo solids. Pseudo, we can say false solids, and super cool liquids, for example glass. Here we have examples: common salt, zinc sulfide, silver, iron, potassium nitrate. Amorphous solids: glass, rubber and plastic. They are amorphous solids. So this is the classification as well as the differences between the two types of solids, crystalline and amorphous. Next is classification of crystalline solids. As the crystalline solids are the true solids, so we will classify only crystalline solid and we will not talk about the amorphous solid from right here now. Next is crystalline solids classification. We have classified on the basis of nature of intermolecular forces between the constituent particles. So here we have four types of crystalline solids. First is molecular solid, second is ionic, next is metallic solids, and fourth one is covalent or network solids that are also called giant solids because they form giant structures. That's why giant solids. In molecular solids, the constituent particles are molecules. In ionic solid, constituent particles are ions, positive and negative ions. They are the cations and anions. In metallic, they have positive ions that are called kernels. Kernels in the sea of mobile electron, delocalized sea of electrons where the kernels are formed. In covalent, they have atoms as the constituent particles. Next is forces. What are the forces? Because we have classified these crystalline solids on the basis of intermolecular forces. So, in the molecular solid, they have various forces: dispersion forces, London forces, dipole-dipole forces, or hydrogen bonds. These are the various forces in molecular solids. Whereas in ionic solid, the forces between the ions are strong electrostatic forces. In metallic solid, they have the metallic bonding. In this covalent, they have covalent bond, the bond formed by sharing of electron. We know that single bond, single covalent bond, double covalent bond, triple covalent bond between the carbon compounds. This is the covalent bond. Next is molecular solids are again of three types: polar, non-polar and hydrogen bonded based on the nature of forces. So there are three types of molecular solids. In polar molecular solids, we have example HCl, SO2. In non-polar, we have example hydrogen and iodine. In hydrogen bonded, we have example ice, H2O. In polar, we have interactions, dipole-dipole interactions. In non-polar, we have interactions, dispersion forces, or we can say London forces. Whereas in hydrogen bonded, as the name is suggesting, the bond is hydrogen bond. So these are the three types of molecular solids. In ionic solids, the forces are electrostatic forces. So they are very strong forces. That's why these are hard and brittle. These solids are hard and brittle. As a result, they have high melting point, high enthalpies of vaporization, and importantly, this is very important point, poor conductor of electricity in solid state. They don't conduct electricity in solid state because they don't have any ions or electrons to move about. So they don't conduct electricity in solid state. In molten state or when dissolved in water, ions become free to move about and they conduct electricity. But in solid state, they are bad conductor or poor conductor of electricity. Here we have examples of ionic solids: NaCl, common salt, KNO3, Na2SO4, LiF. These are all ionic solids. Next is metallic solid. They are the good conductors of electricity and heat. They have metallic luster. They are malleable and ductile. Malleable, that is, they can be beaten into sheets. And ductile, they can be drawn into wires. Examples are the metals and alloys like nickel, copper alloys. In covalent bonding, constituent particles are atoms bonded covalent. They are hard, high melting point, poor conductor of electricity because they don't have any means like ions or electrons. So they are poor conductor of electricity. So we can say insulators. Examples are diamond, quartz, SiO2, boron nitride, Bn. So these are the different types of crystalline solids: molecular, ionic, metallic and covalent, and their examples, and they have different forces for the classification we have decided. Next one is crystal lattice or space lattice. We are talking about the solid state. Solids are also called crystal. They have a shape of crystal. So they have a perfect structure. We can say a lattice. They have certain arrangement of constituent particles for the structure. So crystal lattice or space lattice. What is crystal lattice and what is space lattice? This can be used. Both words can be used for denoting. It is a regular arrangement. So it is a regular arrangement of constituent particles that can be atoms, ions, or molecules. So in 3D space. So regular arrangement of constant particles in 3D space is called crystal lattice. Here we have this diagram, crystal lattice. It is a big crystal lattice, and when we want to study this crystal lattice, we will study the smallest repeating part, which is making the space lattice. Smallest repeating unit of space lattice. This is called unit cell. This is called unit cell. So it is the smallest repeating unit which when repeated over and over again produces the complete crystal lattice. So this is the unit cell. We will study the unit cell. We will study the unit cell. So this is the diagram of unit cell. Here we have edges A, B, C and angles alpha, beta, gamma, which we'll study in the next. What is unit cell? We have learned what is unit cell. Unit cell is the smallest repeating unit that is making the whole space lattice or space crystal lattice or space lattice. So here are the parameters of unit cell by which we can study unit cell. There are two parameters. A unit cell is characterized by two parameters. First is dimension and second is angles. In the crystal lattice, we have the different edges, like we can say this x, y, z. So this is a, b, c. These are the edges. So these are the dimensions along the three edges a, b, c. They can be, may or may not be perpendicular. This is the important point. May or may not be perpendicular. Next is the angles. Angles alpha, beta and gamma that are between the edges. Alpha is between b and c. This is alpha. Between c and a. This is beta and this is gamma. We can say in this anti-clockwise direction alpha, beta and gamma. A unit cell is characterized by 6 parameters. So how many parameters we have unit cell? 6 parameters A, B, C, alpha, beta, gamma. So 3 edges, 3 angles. Total parameter is 6 for unit cell. Next is characteristics of crystal lattice. Now we have learned about unit cell. Now characteristics of crystal lattice. What is the characteristic of crystal lattice? We have drawn a crystal lattice here. Here there are yellow balls. There are 8 yellow balls, 8 corners and 8 yellow balls. Each point in the lattice, these are the points in lattice called lattice points or lattice sides. These are the lattice points or lattice side, which are the constituent particles. And we know that constituent particle can be atoms, ions or molecules. So lattice points or lattice sides. Each point in a lattice is called lattice point or lattice side. Next is each point in a crystal lattice represent one constant particle that I have already told you. These are the constituent particles. These lattice points, these corners are the constituent particles. They can be atoms, ions or molecules. They are the 8 corners. The 3D arrangement represent a crystal lattice. This is the 3D arrangement. Lattice points are joined by, these are the straight lines. They are joined by straight lines to bring about the geometry of lattice. So these are the characteristics of crystal lattice. Each point in a lattice is called lattice point or lattice side. Each point in a crystal lattice represent one constituent particle, that is atom, ion or molecule based on the solid. The 3D arrangement of lattice point represent a crystal lattice. Lattice points are joined by straight lines to bring about the geometry of lattice. This is a diagram and these are the characteristics of crystal lattice. Now next one is types of crystal system. How many type of unit cells are formed? There are two types of unit cells. We have two types. There are basically two types of unit cell constituting different crystal system. These are, first is primitive or simple unit cell, second is centered unit cell. In this, constituent particles are present only on the corners. When the constituent particles are present only on the corners, the unit cell is primitive or simple. This is diagram. We have 8 corners and 8 constituent particles at corners. Next is centered. In centered, constituent particles are present at corners and positions other than corners, means the constituent particle will be present at corners plus at other sides also in the lattice or unit cell. First is body centered unit cell. In this, the constituent particles are present at corner, that is compulsory. And second is they are also present at body center. Look at the diagram. This is 8 corners, 4, 5, 6. This is 7th, 8, and this is the body. This is the body center. So we have this body center. So at the corner plus at body center. Next is face centered unit cell. At corner and center of each face, we have 6 faces. Remember this. It is must for the calculation in upcoming topics. We have 6 faces. So first of all corners 2, 3, 4, 5, 6. This is 7th and this is 8. And for this face 1, 2, 3, 4, 5 and this is 6. So 6 faces, there are 6 constant particles at center of each face in face center. Next is end centered, at corner and center of any two opposite faces. So this is the diagram. At corners we have 8, 3, 4, 5, 6, 7, 8 and any two opposite faces 2. So this is end centered. So these are the types of crystal system. Primitive, only corners, centered, at corner plus position other than corner. Centered, 3 types, body centered, BCC, face centered, FCC, and centered, ECC. In body center, corner plus body center. In face center, corner plus face center of each face, and center, corner plus center of any two opposing faces. Okay, got it? Next is 7 crystal systems. When a unit cell in a crystal lattice has lattice points only at corners, it is called simple or primitive unit cell. We have learned in the previous topic. In all, there are 7 types of simple or primitive unit cells among the crystals. These unit cells are characterized by 6 parameters. We know that A, B, C. These are the edges, alpha, beta, gamma. These are the angles between the edges. So basically 6 parameters. They are called 7 crystal systems or crystal habits. So basically we have the 7 habits of crystals, 7 types of crystal systems. All crystal systems can be placed in one of these 7 crystal systems. So we have these 7 crystal systems. First is cubic. We have axial distances A equal to B equal to C. In this everything is equal. A equal to B equal to C. Alpha equal to beta equal to gamma equal to 90 degree. The example is NaCl, zinc blende and copper. In tetragonal, A equal to B not equal to C. So the condition, you can remember this also. In the first 3, first of all learn the sequence, these 7 types. And starting 3 are equal. 3 angles of starting are equal. So A equal to B not equal to C, alpha equal to beta equal to gamma equal to 90 degree, and these are the important examples. In this 3 are unequal and 3 are equal. Similarly equal unequal, equal. Rhombic sulfur KNO3 and BSO4. In hexagonal, A equal to B not equal to C. This is the similar situation. But here alpha equal to beta equal to 90 degree, but gamma equal to 120 degree. Graphite, ZNO, CDA, these are the examples. In rhombohedral, A equal to B equal to C, but nothing is equal to 90 degree. These are found in the ores like calcite CaCO3 and cinnabar HgS. In monoclinic, A not equal to B not equal to C, these are the last two conditions same, where alpha gamma 90 degree but beta is not equal to 90 degree. Monoclinic sulfur Na2SO4.10H2O. And in the last triclinic, that is the most unsymmetrical, here nothing is equal, not equal to. Like this is the reversal of first and last. Here everything is equal and here everything is unequal. So we have the most symmetrical and most unsymmetrical. This is cubic and this is triclinic. Cubic is the most symmetrical and triclinic is the most unsymmetrical. So these are the 7 crystal systems. Now we have types of cubic crystals and number of atoms per unit cells. First of all, we have written the contribution of each atom to the unit cell. For corner, we will consider the contribution of 1 by 8 because the atom present at each corner contributes 1 upon 8 to the each cube because it is shared by 8 adjacent cubes. So the contribution for one unit cell is only 1 by 8. Similarly, at face, we have contribution only 1 by 2 because it is shared by other faces also. And for within the body, an atom at the body center of unit cell is not shared by any other unit cell and it completely belongs to the unit cell. So the contribution is 1. So at corner we have contribution 1 by 8, at face 1 by 2, and body it is completely 1, not a fraction. So first of all we will take the simple or primitive unit cell. Let's calculate number of atoms present in each unit cell. We know that in simple primitive cell, the constituent particles are only at the corners. So 8 corner atoms into each corner contributes 1 by 8. 1 by 8 atom per unit cell. After cancelling 8 by 8, we got 1 atom. So only corners we have 1 by 8, 1 by 8, and after calculating it we got only 1. So the number of atoms present in each unit cell is 1. Next one is body centered cubic unit cell. In this 8 are present, 8 constant particles are present at corners. We have 8 corners. So 8 corner atoms plus 1 body center. This is the body center. So 8 into 1 by 8 plus 1. This gives 1 plus 1, 2 atoms. Similarly, we have face-centered unit cell. In face-centered unit cell, we have constant particles at the corners plus at the centers of 6 faces. We have 6 faces. So these are 1, 2, these are the corners, 8 corners, and these are faces, 6 faces. So we have 8. We have at the corners 8 into 1 by 8, and for this we have contribution of half. So 6 into 1 by 2. We have 6 faces and the contribution is 1 by 2. So after calculating 8 into 1 by 8 plus 6 into 1 by 2, we got 1 plus 3, that is 4 atoms. So we have 4 atoms in each unit cell of FCC. In BCC we have 2, in FCC we have 4. So these are the number of atoms per unit cell of various cubic unit cells. So here we complete the lecture. Hope you understand the topics, various topics of this chapter startingly. So please like and subscribe the channel for more videos. Thank you very much.